Hello, welcome in the 14th lecture of two-phase flow and heat transfer. Today we will be discussing about mesoscopic lattice Boltzmann methodology. So, at the end of this lecture we will understand the following points. First, we will be explaining the algorithm for solving multiphase flow using lattice Boltzmann methodology. We will be giving you a practice of LBM methodology using a freeware. There we will be showing you how to install the freeware, how to set up the model parameters. I will be showing you also how to run the case study, and finally what results have been obtained and then how to analyze that result, that also I will be showing you. Based on the present experience, you can start performing basic two-phase flow simulations in lattice Boltzmann methodology. So, to give you one outline of lattice Boltzmann methodology, first let us see that what are the macroscopic equations lattice Boltzmann method is solving. Here I have given you one schematic which is lattice Boltzmann equation LBE, which takes information from Navier-Stokes equation and boils down into physical lattice gas automata information. In between it does some mathematical analysis using Boltzmann equation. So, it is a coupling between engineering problem, mathematical problem and physical insight. So, let us see how two-phase flow can be solved in this framework. For two-phase flow, we know that as we are having two different phases, so it is involved with two densities. We consider the higher density of the phases is rho h and the lower density is rho l. So, at the beginning we will be defining two parameters phi and n. So, phi will be nothing but rho h minus rho l divided by 2 and n will be rho h plus rho l divided by 2. For example, let us say you are dealing with air and water. So, air will be something around 1 kg per meter cube and water will be 1000 kg per meter cube. So, you will be finding out that this n will be becoming 1000 plus 1 divided by 2. So, that means something around 500.5, okay, and your phi will be becoming 1000 minus 1 divided by 2, that means 499.5. Okay. Next, let us see the governing equations which are required for solving these two-phase flow examples involving, let us say, gas and liquid. So, first we will be having two different equations for both the phases, that means the gaseous phase or liquid phase. It can be some other two-phase flow problem also, solid liquid or solid gas situations. So, if we have two continuity equations, and if you remember your continuity equation formats from your fluid mechanics analysis, then you will be knowing that if we add both the continuity equations for gaseous phase and liquid phase, two different phases, then we will be getting some equation like this del del T of n, where n is nothing but rho h plus rho l divided by 2 plus del of n into u is equals to 0. So, basically if you see the continuity equation for individual phases, n will be replaced by rho h and rho l respectively. So, once you add those two equations, you will be getting one equation with n. And if you are having any phase change in this equation, obviously the phase change will be having same magnitude but opposite in sign. So, once you add those two, the right hand side will always become 0, right. Similarly, one can write down the Navier-Stokes equation. So, you know that two Navier-Stokes equation, that means momentum equations we will be having for gas and liquid. Once we add those two equations, we will be once again getting a equation having n as parameter. Okay. So, in the left hand side we are having unsteady and inertia term, and then in the right hand side we are having pressure gradient term over here, viscous term over here, buoyancy term over here. Apart from that, we are introducing two new terms. Okay. These are coming due to your chemical potential coming from your chemical thermodynamics. So, if you write down species based momentum equation, then this chemical potential terms will be coming into picture. Okay. In a similar fashion, if you are having energy involved, so you can find out the energy equations and for both the phases and add those, you can write down energy equation in this way, where in the left hand side you are having unsteady and convection term, in the right hand side you are having conduction, and if you are having any heat generation, right. So, in LBM framework, first we in LBM two phase framework, first we convert individual phase equations to some n equations like this. Okay. So, continuity equation involving n, Navier-Stokes equation involving n, and finally, if energy is there, energy equation involving n. Okay. So, where n is nothing but rho h plus rho l divided by 2. Next, let us see for capturing of interface in Lattice Boltzmann methodology, we are having basically two approaches. First one is sharp interface. Sharp interface means if you are having a sudden jump of the interfacial properties, that means let us say density or viscosity, whatever you consider, if we consider that the interface is very thin, okay, so across the interface there will be a sudden jump of the properties. Okay. So, let us consider this is density contour, variable is density. So, this side we are having gaseous and this side we are having liquid. So, there is a sudden jump across this interface. Okay. So, that kind of thing we call as sharp interface concept. On the other hand, another counter argument is there where people consider that the interface is not sharp, that is diffused over a finite thickness. So, here you can see using color gradient we have shown the sharp change of color, here it is gradually changing. So, the variable here also we have shown that it is gradually changing over a small thickness. Okay. So, that thickness is called interface thickness. Now, in this methodology, this Lattice Boltzmann two phase methodology, we always consider this diffused interface, and for that we need to consider our Cahn-Hilliard equation for interface capturing. Okay. So, Cahn-Hilliard equation, if you write down for gaseous phase and liquid phase separately, and if you subtract, then you will be getting additional equation involving phi. Okay. So, del phi del T is nothing but your unsteady term, here you are having convection term, and on the right hand side you will be having a term involving the chemical potential, where mu phi is the chemical potential and theta m is actually mobility of the interface, that means how easily you can change the interfacial configuration, right. So, altogether if we are having energy involved, we will be getting 4 equations are there. Okay. So, continuity equation involving n, momentum equation, energy equation, and apart from that we are also having one equation called Cahn-Hilliard equation involving phi, right. Now, let us see how the domain of our simulation can be discretized in Lattice Boltzmann methodology. For example, let us say this is our domain, a rectangular domain to start with. So, what we will be doing, this domain we will be discretizing in small volumes or small lattices rather in this case, because in Lattice Boltzmann we consider that the domain is actually discretized with lattices. So, here all these are actually individual lattices. The discretization pattern will be more or less similar as we have seen in case of your finite volume or finite difference methodology. Only difference over here is that in finite difference and volume you can go for non-homogeneous discretization, but here in Lattice Boltzmann till now we are having provision for homogeneous discretization only. So, you see uniform size of lattices we will be giving inside the domain, right. Now, always Lattice Boltzmann is having certain mechanism to carry forward the information. So, those information will be actually the some information for your governing equation parameters, that means your rho phi and n in these equations. So, what we will be seeing, let us say some information is being generated over here in the center lattice. So, this equation can flow depending on the lattice configuration in a particular directions only. Here I have shown you one typical example of D2Q9 structure which I will be explaining soon. So, here you see the information which is being generated in this lattice can stay inside the lattice only. So, this is the first possibility, and you are having all other 8 possibilities also. So, going horizontally left, going horizontally right, moving up, moving down, and 4 corner directions. So, all those 8 directions you are having apart from staying in the own cell. Okay. So, all these 9 directions are possible. So, those actually information directions are actually first captured before streaming. Okay. So, those are actually called collision stages. So, after collision the information will be propagating depending on the streaming. So, what we do after deciding that which direction it will be going, the information is actually propagated due to propagation. Okay. So, here you see we have shown after propagation what happens. So, earlier this was our lattice of concern. Now, you see left hand side horizontal direction has moved in the immediate leftmost lattice. Similarly, right hand side direction has moved to immediate rightmost lattice, and then top directional information has moved to the upper lattice, down directional information has moved to lower lattice. Like that the corners has also taken the respective directions. Okay. So, if one information is being generated in the center cell, it propagates in the neighboring cell in this fashion, okay, depending on only the lattice structure whatever we consider. Here we have considered a D2Q9 lattice structure. So, these two steps are very important. First one is collision and second one is propagation of information depending on the specified directions. Okay. Then let us see that what are the lattice directions possible. I will be showing you here only few, but there are many more like this. So, first one is over here D2Q9, which I have already showed you. So, this is the 0th direction, apart from that 1, 2, 3, 4, and the corners are 5, 6, 7 and 8. Okay. So, 9 different directions are over there. Okay. In a similar fashion, in 3-dimensional lattice if we consider, that means if the problem is 3-dimensional in nature, we will be having D3Q19 structure. Okay. So, here I have shown the schematic nature of the lattice directions in a cube, and different directions are marked as 0 to 18. Okay. So, you can find out that what are the different lattice directions, right. Now, after discretizing this domain with 2D or 3D lattices, next our task is to find out how to discretize the governing equations, which I have told in the previous slides, that how to discretize those in these lattices. Now, for discretization, as I have told you that it is involved some sort of collision. So, we need to find out what is the probability density function for the collisions. Okay. So, we have to go for some distribution functions over here. Okay. So, for each equation, information propagates information how it will be propagating due to collision between the lattices, that will be found out by these probability distribution functions. Now, here as we are having 4 equations, we require 3 probability density functions. Okay. So, those are F, G and H. Okay. One by one I will be telling you the essence of this F, G and H. First let us take what is F. Okay. So, F is actually actually one probability density function whose summation will be giving you one macroscopic variable n. Okay. N, if you remember, I have told that one is rho L plus rho H by 2. So, summation of F of all different directions depending on the lattice structure whatever you have taken. Okay. I can write down that is equals to n. So, that means in D2Q9 structure, starting from F0 to F8, we are having, if we add all those F's, we will be getting the macroscopic property n. Okay. In a similar fashion, you know, U can be obtained in this fashion, where Fi already I have explained, Ei, that is the lattice directional velocity. So, for example, let us say over here for D2Q9 structure, the 0th direction is having 0 0 velocity, 0 0 velocity x and y direction, and for 1 it is having plus 1 0, for 2 it is having 0 plus 1, for 3 it is 0 minus 1 0, and for 4 it is 0 minus 1. Similarly, for the corners it is having 1 plus 1, plus 1 plus 1, then it is minus 1 plus 1. Similarly, you can find out the C7 and C8 directions corresponding E's. So, we know what is the E direction. So, we can add this Fi into Ey. If you are interested in x directional velocity, always add that x directional velocity component. If you are interested in V, that means the y directional velocity component, then you add the y directional velocity. Okay. I have already spoken that how x and y can be designated in D2Q9. On the other hand, here we are having some terms which were there in the macroscopic equation. This is coming from the chemical potential term, and this is your body force. If your problem involves body force, those things will be coming over here. So, that means in using F, only by knowing the distribution F, you can find out N and U. Okay. In a similar fashion, this G will be giving you phi and H will be giving you T. So, summation of G of all directions will be giving you phi and summation of H in all directions will be giving you T. Now, whenever we will be adding the informations, one important parameter we need to take care of, that is what is the weight of different directions. So, weights are typically specified whenever we define the lattices. Usually the weights we give as for D2Q9 4/9 for the 0th direction, 1/9 for the 1, 2, 3, 4, that means horizontal and vertical components, and 1/36 we give for the corner components, that means 5, 6, 7, 8. Okay. Similarly, for the 3 dimensional lattice structure D3Q19, weights are defined in this fashion. Okay. Already I have told you about EI, okay, which is nothing but directional velocity. So, velocity can be written in this fashion in terms of cosine and sine. Okay. I have already told you the magnitude 0, 0, plus 1, 0, 0, plus 1, something like that. So, if you replace these things, okay, by I by the corresponding number starting from 1 to 8, you will be getting those values once again back. Okay. Next, let us see the algorithm by which we can go for lattice Boltzmann calculation. As I have already told you, first we need to define what is phi and n. Apart from that, we need to get all other physical properties also, starting from the chemical potential, because it is involved in Kern-Hillard equation. So, you see mu phi, which can be found out in terms of phi's, rho h minus rho else, and few other terms. For example, K, A, those are constants. Okay. So, those actually are found out based on some other physical properties of two phase flow. For example, here K and A can be found out from the interface width. If you remember, in case of diffused interface, I have talked about over here that if you are having diffused interface concept, what is the thickness by which the fluid property is changing from one phase to another phase, that is the interface width W, as well as we know that surface tension will be applicable in the interface. So, from the knowledge of W and sigma, okay, for your problem, you can find out what is K and A. Okay. So, those K and A will be important for getting the macroscopic parameter mu phi or chemical potential. So, how to find out what are the relationships between W and K with K and A with W and sigma, those are given over here. So, once you know the macroscopic properties, you can easily find out K and A, and hence you can find out the chemical potential mu phi. Okay, next I will be showing you over here what is the discretized equation. So, this discretization is actually following Lattice Boltzmann discretization, that means your lattice gas cellular automata formulations. As you know that in volume of fluid method, this finite volume method, we go for Taylor series expansion. In case of Lattice Boltzmann equation, we go for Boltzmann approximation. Okay. So, here after doing this Boltzmann approximation, what we find out, the distribution function f is actually can be written in this fashion, where you see this is the temporal part of change of f. Here we will be having the convective part. Okay. Here we are having some sort of external force field part, and finally here we are having the collision operator. This collision operator is very, very important, because we are having always the collision between the lattices. So, once we have the collision operator, here I have shown what is the nature of the collision operator. So, collision operator always depends on the present value of the distribution function and the equilibrium value. Okay. So, equilibrium value means at whenever the system is almost in equilibrium. So, in that condition, what was the properties of the, what are the value of the distribution function. So, that I write down here as FEQ. This is also very important factor, which is called relaxation factor tau, relaxation time tau. So, this will be also coming into picture in case of collision operator. Now, here I have shown how to find out the equilibrium distribution function. You see, equilibrium distribution function is dependent on the time, dependent on the temperature, as well as it is dependent on the velocity and density. So, once you know the macroscopic property of the problem, easily you can find out what is the equilibrium function of the distribution parameter. Okay. And this tau is actually dependent on the fluid property. For example, for momentum equation, this tau will be dependent on the viscosity. For energy equation, tau will be dependent on your thermal conductivity, and so on. Okay. So, once we put this collision operator over here in this equation, we get simplified equation of f. Okay, that means at next time step. So, you see t plus delta t, that means next time step, and x plus ei delta t, that means after propagation. So, this is after propagation. Propagation scheme I have already shown to you. You will be finding out it is dependent on Fi and then delta by tau Fi minus Fi equilibrium. Fi equilibrium already I have shown you how you can calculate in case of your Navier-Stokes equation. It is dependent on your u, the velocity of the lattice, macroscopic velocity of the lattice, density of the lattice, and then sound speed c. Okay. Apart from that, Wi, the weight factor of different directions, will be also coming into picture. Okay. Next, let us see similar type of equations for G and H. So, I have already told you G will be important for finding out the interfacial location, and it will be giving you summation of G will be giving you the value of phi. So, here also you see G I after collision and propagation, you can write down as G I x t plus G I minus Gi equilibrium minus Gi by tau phi. Remember this tau phi, and in the previous here tau, these are not equal. This tau phi will be dependent on the fluid properties, and tau will be also dependent on fluid properties, but their functional natures will be different. So, here also what is the value of G equilibrium I have shown you over here. So, these are dependent on lots of empirical values Ai, Bi and Ci. So, those can be found out once you go for a detailed description of the lattice Boltzmann equation. Okay. Here I have not described all those issues. Similarly, you can find out the discretized equation for H. Here you see this is H after propagation and collision, can be found out once again from the H equilibrium, and tau T. This tau T is dependent on the thermal conductivity. Okay. And equilibrium once again can be written in terms of the temperature of the lattice velocity. Okay. Obviously, Cp or specific heat at constant pressure will be coming into picture along with Wi. Okay. So, here once again I have shown you 3D nature of the D3Q19 structure along with the velocity vectors. Okay. So, u, v and w I have shown you over here. Okay. Now, I will be showing you in detail that how lattice Boltzmann equation can be solved using some open source software or freeware. There are different freeware available in open source which you can use. So, some of the freewares are like this: Palabos, OpenLB, Taxila LBM. So, all these are dealing with LBM simulations of two-phase flow, but today I will be giving you some example of using Palabos. So, this will actually give you some sort of chance to do some sort of small simulation of two-phase flow and practice this one. So, let us see Palabos. To get it started, you need to know that it runs in Linux platform, Unix platform, okay, and you need to install C++ library, that means G++ or GCC library, which already I have shown you how to do. Okay, then let us see how to install the Palabos in Linux. So, first you need to download the software. Okay, so it will be downloading some Palabos version .tgz format. Okay, so it will be downloading. So, where from you need to download, that also I have given you over here. Then you need to untar or unpack the software. So, what is the command for untarring and unpacking the software, that also I have given over here. Now, you need not to install this software because this library is compiled on demand. Okay, so, installation is not there. So, whenever required, whenever you will be trying to run the code, it will be compiling the code on demand. Okay, so, whenever applications, user applications are there, it will be doing the compilation on demand. Next, let us see a case study using Palabos. So, what we will be doing over here, first case study we will be seeing over here for colliding bubbles. Let us say we are having two bubbles which are colliding amongst themselves. Okay. So, a series of instructions we will be writing in a .cpp file. Let us name that CPP file as two bubbles.cpp file. Okay. And then we need to run that code, okay, using some makefile. So, makefile you can find out in the same directory where you have actually stored Palabos. So, you can go in that directory and find out that makefile which is already existing. Then what you need to do, you need to go to that folder, okay, where this .cpp file has been saved. So, how to go to that folder using cd, that I have shown you over here. Okay. Then how to run that executable file using makefile. So, you have to just give the command make. Okay. Once you give the make command, it will be developing the executable files. To run that executable file, what you need to do, you need to give a command like this /2
2 bubbles, that is the name of the CPP file, and then few parameters. So, first parameter is 1 into 10 to the power minus 4, which is nothing but the value of surface tension, then 5, which is nothing but the thickness of the interface, okay, around the bubble, and then we are having 15, which is nothing but the radius of the bubbles, okay, which are colliding, and then TMP is the output directory where it will be writing the results. Okay. Next, let us see little bit of code. So, here I have first shown you the main code, main points I have highlighted over here. You see this is the line written in the C++ version, what is the main code, int main, that means this is the main code. Next, I have shown you some enlarged portion over here. You see this, here we are doing some functions, that means initialize parameter, here we have initialized the bubbles, I will be showing you. Then create fields, so I have to create the fields which are important for here it is F and G. And then create processor arguments. So, which processor, if it is parallel simulation, which processor will be doing which component, that we create over here. Initial conditions, that means where the bubble will be staying initially, what are the velocity and temperature conditions, those will be giving over here in initial conditions. Add coupling, so here we can add coupling between different equations. Let us say we are having F equation and G equation, so we can add coupling between F and G. Then you see here we have run the time loop, that means we have to advance forward in time so that the bubbles can come closer to each other and collide. So, we have started from iteration 0, that means time equals to 0 to some maximum value max iter, okay, in the steps of 1. So, it will be doing the time limit. Okay. And then you see here in this loop we have written the external file, all the informations in different time steps we have written in some external file so that we can visualize the result. So, here you see we are write GIFS at every iteration and write VTK scalar field. So, VTK scalar field is important for seeing the result or contour in some external software like ParaView or something like that. So, here we are writing the external files, okay, all the results. Then here what we have done, these are very important. So, for G equation we are colliding and streaming. So, we will not be going in detail of this function collide and stream, but here we are adding the equations, and for then F equations will be going for colliding and streaming. Okay. So, each time step this F and G equations will be colliding and streaming. Okay. Next, let us see little bit part of the initialization, otherwise things will not be clear. So, here you see in this part I have shown you that you can give what is the max iteration, that means maximum how much time the code will be running. Here I have given 20,000. Nx, Ny, Nz, these are the actually domain size. Okay. So, you are having 251 as length, 151 as width and 151 as height. So, okay. So, it is actually 2:1:1 ratio, the domain. Okay. Then here we have given, you see, CXO, CXY and CZO, these are actually the center of the bubbles. Okay. So, CXO is x coordinate, YO is y coordinate and ZO is the z coordinate. So, we have given all this CXO, CYO and CZO in terms of Nx, Ny and Nz. Then here you see in this loop we have given the density and viscosity values. Okay. So, density ratio we have taken as 10, viscosity ratio between the fluids we have taken as 10, and here we have given some other parameters also like initial velocity, Peclet number, okay, and we have also given what is the density of the highest density fluid and what is the density of the lowest density fluid depending on the density ratio 10. So, this is rho h by density ratio. Similarly, the viscosity is tau 1 we have considered as 0.5, and similarly tau h can be calculated by nu h by rho h into 3. Okay. So, nu and tau, those are kinematic and dynamic viscosities. Okay. So, for higher fluid and lower fluid we have shown you over here. Next, let us see the initial position of the bubbles. Actually, we are solving this kind of simulation. So, here you see we are having elliptic bubble over here, another elliptic bubble over here. In this side we have given some velocity towards right, here we have given some velocity towards left, and we have shown how they can collide. To show that, you see over here we have given that what is the concentration. So, this is actually definition of your phi and your n. Okay. So, this is n, this is phi, and here you see we have given the bubble contour. So, first equation if you see, this is actually 2 into x square. So, 2 into you see x square. So, that means this bubble we have given, this ellipsoid we have given, and second one TC2 you see we have given 2 into y square. So, that means ellipsoid in the y direction we have given. Okay. And then here we have given the initial condition, you see here we have given for the first bubble. So, bounding box we have created in the left hand side. So, you see over here we have given the velocity as 0.02, okay, and for the another bubble we have given minus 0.02. So, first bubble is moving, the left hand side bubble is moving towards right hand and right hand side bubble is moving toward left hand, okay, so that they can collide. Okay. Then I have shown you some result over here, you see we have started from this configuration, okay, as time progresses they are coming towards each other. Here they have started merging off, here they have merged and taking the final shape, slowly progressing like this, and finally you see due to surface tension it is becoming one union bubble, okay. So, starting from two bubble situation, how bubbles are colliding and they are merging, that we have shown over here. So, the steps of the code also I have explained. So, if you want you can have a look at this one and practice this LBM simulation. Okay. So, let us summarize this lecture. In this lecture we have elaborated mesoscopic lattice Boltzmann methodology along with the constitutive equations, mass momentum and energy equation related to probability density function we have described. We have also shown you one freeware called Palabos, and the use of Palabos for this lattice Boltzmann equation we have showed you. Okay. And then in this Palabos freeware we have shown from installation, setting the model parameter, how to run and how to analyze the results, those things we have shown over here. So, apart from Palabos you can try any other freeware or some software you can use for practicing this lattice Boltzmann methodology. Okay. So, let us test your understanding at the end of this lecture. As usual we are having 3 questions over here. First one, mention valid 2-dimensional lattice structures. We are having 4 options over here. To remember 2-dimensional lattice structure. So, we are having D2Q7, you know that 2 symbolizes the 2-dimensional nature. So, D2Q7, D2Q9, D2Q17 and D2Q5. Okay. So, already we have shown you D2Q9 is probably the correct one, but you will be finding out that if you reduce the corner directions, then D2Q5 lattice structure is also possible, which I have not shown you in this lecture. But if you remove the corner directions and only keep the horizontal and vertical positions, this will be D2Q5 position. So, the correct answer will be B and D, both D2Q9 and D2Q5. Other two cannot be accommodated in 2-dimensional structure. Next, summation of Fi is equivalent to, this is very simple, I have already told you that summation of Fi will be equivalent to, we are having 4 answers U, T, rho U and rho, all of we know that summation of Fi will be equivalent to your rho. So, D is the correct answer. How many probability distribution functions are required to capture diffused interface in a melting process? So, melting process means it will be involving heat transfer as well as interface. So, it will be diffused interface concept, okay, as well as we are having definitely the continuity and momentum equation. So, we are having your continuity momentum equation, energy equation and diffused interface equation. So, we are having options as 0, 1, 2 and 3. So, definitely correct answer will be F, G and H. So, correct answer is 3. Okay. So, with this I will be ending this lecture. Thank you.